So in the first video, we established that we know from lecture that we have ruin if the thing that we defined as W in the first video exceeds U. And also that we had established from lectures that W satisfies a stochastic fixed point equation that is defined here. Now what Kesten Goldie tells us is if W satisfies a stochastic fixed point equation, then we can conclude that the tail of W is asymptotically of polynomial decay if a lot of things are satisfied. So this is the result that is interesting here. And in order to use this result, we have to check some assumptions. And while we check these assumptions, we will also calculate the value of this rate of polynomial decay here. So from from Jeffrey's notes, I can see that the first assumption to check is whether there exists a positive random variable A such that the function phi governing the stochastic fixed point equation evaluated in V is roughly equal to A multiplied by V for V sufficiently large. Now let us try to check that in our case. In our case, we have that phi evaluated in V is equal to AL plus A multiplied by the maximum of V and 0. Now what happens as V becomes very large? Well, when V becomes very large, this term here takes over, right? And essentially what you have in this here is you want to show that phi of V is equal to AV plus something that goes towards 0. So what we can notice is that this thing here divided by V is equal to AL divided by V plus A multiplied by max of V and 0 divided by V. Now as V tends to infinity, the max of V and 0 of course just tends to V, and the second term tends to A. Whereas the first term tends to 0. So when V tends to infinity, this entire thing here tends towards A. And what this means is that phi of V is asymptotically equivalent to AV as V tends towards infinity. And therefore, we have now established what we wish to check in the first assumption. Now for the second assumption, what we want to check is, well, we actually want to check a lot of things. First of all, we want log A to be non-arithmetic. What that means is we want to check that log A is not something that takes values on a discrete grid of values, but that's completely okay for us because log A is, well, let's just write this up here. Log A has the same distribution as log AI, which is equal to log of 1 over Ri, which is equal to minus log of Ri, where you know that Ri is log normally, where you know that log of Ri is normally distributed, and therefore this has continuous distribution. And therefore we are safe. So log A is indeed non-arithmetic. There is one more thing that we also need to check in part 2, which is that the mean of log A is smaller than 0. So let us just check that as well. We've already established that log A has the same distribution as minus log Ri. So that means that the mean of log A is equal to minus the mean of log Ri. And log Ri is normally distributed with mean 1, so this is just minus 1, which is indeed smaller than 0. Now let's trudge on in part 2 here, where we want to check whether there is a positive solution to the cumulant generating function of log A. So there is a positive solution to the equation log of the mean of e to the r log A equal to 0, where in this exercise here we denote this cumulant generating function of log A by the typical symbol that we use for cumulant generating functions. So let's just try to find this positive solution R. If we calculate this here, then you first can notice that log of A, again, has the same distribution as minus log of Ri, where log of Ri is normally distributed, and therefore log of A is normally distributed with mean minus 1, since this has normal distribution with mean 1, and the variance is unchanged. There we go. What we want to do now is, sorry for the pause there. What we want to do now is we would like to calculate the cumulant generating function here. And if you just find the cumulant generating function for a normal distribution with these parameters, then what you get is that it is given as minus r plus r squared halves. And if you set that equal to 0, then that implies that r should be equal to 2. There we go. So it is indeed true that there is a positive solution to this cumulant generating function here. There is still one last thing that we need to check according to Kesten Goldie, and that is whether or not the cumulant generating function in R is in fact smaller than infinity. So is the cumulant generating function is the derivative of the cumulant generating function in R in fact finite? And what we can see here is differentiating this expression up here, what we get is minus 1 plus, well, what do we get here? 2r divided by 2, so plus r. And since r is equal to 2, what you get is 2 minus 1, and that's 1. Yay! So this is indeed a finite value. We have now checked 1 and 2, and essentially if you're really good, you also want to check 3, but 3 does involve a rather complicated expression, because if you look in the notes, then what you want to show is you want to show that the mean value of phi evaluated in W to the R power, so squared, minus A multiplied by the positive part of W squared. You want to show that this thing here is smaller than infinity. And the thing that makes this hard is it is kind of hard to talk about the distribution of W, because we don't know about the distribution of W. So let us just assume this is satisfied. Because what happens now? If we assume this is satisfied, then we have checked all the 3 conditions that need to hold for us to apply Kesten Goldie. Then what we get essentially is this. Then the Ruin probability, which for us is given by the probability that W is greater than U, then this Ruin probability is asymptotically polynomial with a decay rate of minus r. And our r is 2, so we have u to the minus second. The c component here is actually given by calculating this thing. It is immensely hard to calculate, so we will not do that. The interesting thing to look at instead is the rate of decay 2. Because where does that number come from? Note, the number r equal to 2 is a direct consequence of the calculations we did calculating the calculations we did based on the cumulant generating function of log A, which we established depended only on the distribution of the returns. So the number r equal 2 is a direct consequence of the returns being log normally distributed. Therefore, the rate of decay, well, it does not depend on anything else. Which means it does not depend on things such as premium. It does not depend on things such as the claim size distribution. And that is pretty significant because it means that even if we set the premium to 0, so even for C equal to 0, we still have that the Ruin probability asymptotic value is unchanged, thanks to, in large part, the stochastic returns from the investments. So what should you take with you from this exercise? How to apply the Kesten Goldie theorem, mainly. And one more thing is that while we have used the stochastic fixed point equation that was derived during lectures, we have actually not gone in and tried to derive that equation again. It's a really good idea to go through the lecture notes and work through that equation, work through the proof for finding that stochastic fixed point equation on your own in cases where you do not have a recursive equation given in a problem, or if you have no guarantee that the limit for your recursive equation exists, then it can be necessary to go through the motions of the kind of proof that yields the stochastic fixed point equation that we have in this exercise.